Any questions so far? Okay, so do you like this tool? I like it, but not so much. Why? Because it's not analytic. It gives me, it fritters away the beauty of analytics. So it's numerical all the way. I can give you an example, quick example. So this is the inverted pendulum that we started with, the video in the beginning of the lecture. So this is mass, theta, L, and we have oscillation here up and down, Z of t. So Z of t, say it's something cosine omega t, and let's have it negative, doesn't matter. The differential equation, which most of you guys take it 241 and did it as a quiz, was theta double dot is G over L sine theta. This is reminiscent of the pendulum dynamics, and you add to it Z double dot, the other acceleration, also sine theta. Okay? So substitute with Z, you get G over L, and I'll take the sine theta common factor. So this is plus omega squared Z over L cosine omega t times sine theta. And I know that this system, if I vibrate it strong enough, it will be stable, right? So we can assume small angle approximation, because at the end of the day we're going to linearize. So linearizing at around this equilibrium, which is the origin. So sine theta is approximately theta of the linearization. And now I can write my linear system, theta dot is theta dot. So the first equation, theta dot, is 1 here and 0 over there. The second equation is G over L times theta plus omega squared Z over L cosine omega t. So there is time variation here and it's time period. 0 and this 0, this last 0, you can add some damping if you like. So you can, or damping. So negative mu.
There's no theta.
Yeah, thank you. Okay, so it's clear that this is indeed A of t with A is time periodic. Go and simulate for two initial conditions, 1, 0, 0, 1. For just one period, get your matrix, check the eigenvalues. You can determine what? I can only determine for a given frequency, amplitude, and length, gravity of course, that this system is stable or not. This is all what I can determine. But I cannot determine, well, do I need to increase omega or not? Do I need to increase Z, L, whatever? If I want to increase it and check the gate. So there is no physical insight into the system dynamics. It's just a blind machine. You give it the parameters of the system, it replies back with stable, unstable. So it's a very powerful tool, and if you have a very large system and you don't have an analytical form for the system dynamics anyway, this is the way to go. So it's like almost, most of the analysis of time periodic systems, helicopters or whatever, vortex shading, you name it. It's Floquet theorem, and if they are not doing Floquet, maybe they are doing something wrong. Okay, so but a good chunk of people like analyticity, and I'm one of them. So we'll consider some analytical tools, which is the averaging theorem. It applies in a special case of systems on this form. So x dot equals epsilon f of t, x, and epsilon. F is t periodic in t. And I will call this system 2a for averaging. So it's a nonlinear time periodic, but special case. What do you mean? First of all, epsilon, as it may indicate from now, epsilon will be a small parameter. So all the ensuing analysis is valid for a small enough epsilon. So epsilon has to be small. So when you see this form and the epsilon is small, this is from the get-go, it's for weakly nonlinear systems or for weakly forced systems. So the system has its own dynamics, and on the top of that you perturb it with weak forces that are time varying. Okay? So yeah, and this is, I mean, this is based on the perturbation theory. So that's what I'm saying. It's you perturb your system with a weak thing. But the theorem is useful. So let's see and how we make it useful. But this is the essence. If your dynamics is not in this form, you're applying on your own. This theorem doesn't hold because many people do that. So like, you know, like tens of papers in flat and flight dynamics, we applied or they applied without having the system on this form. The ensuing analysis is not necessarily correct. Okay? So if this is the case, then here is the theorem. We have two parts. What is the first part? If x of 0, the initial condition for the system. Oh, first of all, I need to define the average dynamics. So here is the original dynamics, nonlinear time periodic. Define the average dynamics, which is simply average. It's super easy. The averaging is really very, very complicated. The average dynamics, just average over the time. So this is equal now epsilon f bar of x bar, where f bar is just the average, so the integral over the period of your dynamics, held in x constant. So just ignore x. Any function of t, average out. Cosine gives you 0, sine gives you 0, cosine squared gives you half. That's it, super easy. Add 0 in, okay? So, and substitute epsilon 0 there. I will call this system 2 bar for the average dynamics. So here is the statement of the theorem. If x of 0, the initial condition for the original system, minus the initial condition for the average system, they are close enough, they are of order epsilon, then there exist b and epsilon star such that the solution of the original system and the solution of the average system, they stay close together for all t, not all time forever, but for time long enough. Remember, this is an important distinction because, let me just write it, it's 0 and b over epsilon. We already expect that if I have a system and I perturb it a little bit, okay, the two solutions will be close for some time, for sure, for some time. No matter how small it is, right? But the point is to ensure this closeness for a long time on the time scale of 1 over epsilon. Epsilon is very small, so this is a bit large. It's not for infinite, it's not for all time, but for some long time, okay? On the time scale of 1 over epsilon. And this is not for any epsilon, it's for all epsilon here. You might wonder, I'm keeping stressing epsilon, epsilon. What do you mean by epsilon? Typically, in engineering applications, epsilon is related to the reciprocal of the frequency. I am exciting my system. If I'm exciting too fast, epsilon will be too small and this will work. Okay? This matches the engineering intuition. Remember any mechanical system. Any mechanical system. So it depends on how you guys view it. You know what's this? Then draw any axes or something. Okay, what do you think? So this is the boogie or the frequency response of a typical mechanical system. Any mechanical system, you just this guy, this guy, this guy. Any mechanical system, you would have something. Maybe you have some peak here, but it will decay as, you know. So this is, if there is no log here, so this is really 0. What is this g? The g is you're inputting a sine omega t or cosine to your system transfer function g, and you're getting what? Also sine with the same frequency because it's a linear system. There is some phase shift, ignore it for the moment, but the amplitude is different. The amplitude is a multiplying by this g. So this is your amplification or attenuation. if one says here, and this is 0, it seems that for very high frequency, I'm multiplying any mechanical system by again 0. So after some frequency, you're exciting your system too fast, the system doesn't feel your excitation and gives you the mean value. The mean value of sine is 0, so it will give you 0. Okay? So the idea of averaging matches very well the intuition here. But it has to be made very rigorous, otherwise you will go with your intuition and you will be completely wrong. I will show you a statement next time. So what we're saying here is, if we start close enough, order epsilon, they will remain close enough, order epsilon, for some long time. But this epsilon, which is the reciprocal of the frequency, it has to be very small, or small enough. So the frequency has to be high enough. The main question is, how high is high enough? How small is small enough? We really don't know. This is the main issue behind averaging. It says there exists some epsilon star such that your thing will value below this value. So in the language of omega, there exists some omega star such that if your omega is larger than this frequency, this will hold. But how high should I go? We don't know. So this is the point. You do it with the highest possible thing, and you hope that you match it your omega star or epsilon star. Double I, here we have the stability result. This is just the closeness of the trajectory. Here's the stability result, which is interesting. So if x naught bar, some equilibrium, is the average dynamic has no time. Okay? So we're talking about fixed points. Is an exponentially, has to be exponentially stable, by the way. So via linearization, has to be exponentially stable. If x naught bar is an exponentially stable fixed point or equilibrium point, we're talking about a point of the average dynamics 2 bar. And if we stay close enough, if we start close enough, so x of 0 minus x bar of 0 are of order epsilon, then there exists epsilon star, the damn epsilon star that we're talking about, such that x of t minus x bar of t, they are of order epsilon for all time. So stability gives you the matching for all time. That's very good. But still, it's not for any epsilon, it's for epsilon in this thing. Okay? Epsilon has to be small enough, must be small enough for this entire thing to work. This comes from perturbation technique, and perturbation technique, the entire theory is just based on small perturbation. Here I can add that, moreover, the system, the original system, which was what, 2, I guess? 2 averaging. The original system, the nonlinear time periodic system, has a unique, exponentially also stable, periodic solution, xt, with satisfying that the difference between xt and this equilibrium point of the average dynamics is bounded by epsilon, okay, for some k. So I'm orbiting around the equilibrium point of the average dynamics. Let's recap here what. I don't think we will have time to give an example for averaging. Actually, we may. Let's see. Let's get the same example. So the inverted pendulum, mass L theta z, and z is z cosine omega t. Should we get the example or compare between Floquet and averaging? What do you like? Do you like to see the example for averaging, or do you see the comparison between Floquet and averaging? Next time we'll do the other one. Example, okay. So let's see. So here is the differential equation from above. It was G over L plus, I guess, right? Z omega squared over L sine theta, and there is cosine force here, cosine omega t. I must write my system on this form, which is epsilon times something. So I need to define my epsilon from the beginning. From the get-go, you need to do scaling. The issue is that people do averaging without scaling. Let's average out. Let's do what they call crude averaging. If you do crude average, just average out. So theta double dot equals G over L sine theta. And here this is cosine omega t. You average cosine, you get 0. So there is no stabilization, nothing. You lose the entire thing. It's really silly. Sometimes the dynamics is very rich such that you even get something with crude averaging. And I'm telling you, tens of papers on flat and flat dynamics is just do crude averaging. We must write our system in the perfect form first, okay? Or if you want to do crude averaging, okay, but it can't be like this. It has to be like maybe higher order averaging, maybe something else we're going to introduce next time. But it cannot just be like this, okay? So you have to have it on the specific form. So we need to define our epsilon. So if we're saying that it's small amplitude, so Z may be divided by L, I will define this to be my epsilon. Okay? Also, I know that this is my dynamics. What is the time scale of my dynamics? This is the pendulum. So if there is no oscillation, it goes on its own with the natural frequency, omega naught, which is square root G over L. Okay? My frequency must be much higher than omega naught. So omega over omega naught should be scaled with epsilon. So it's maybe something alpha times epsilon. Should be scaled with epsilon. Should be, I'm sorry, 1 over epsilon, right? Because this is, or let's say this is omega naught and this is omega naught. Okay? Let's write it as delta, just to match what is in my mind. Any questions so far? Okay, so let's do that. So I have, I'll substitute these guys. Here I have theta double dot equals, I will divide by omega squared, I'll take omega squared as a common factor. So here I have G over L, which is omega naught squared divided by omega squared. Plus, Z over L is already epsilon, I said that, cosine omega t. So, this guy is omega naught squared, this is delta squared epsilon squared. There is a usual trick that we always do when we need to generate, remember that we need to generate what? We need to generate this form. We need to generate this form. So something first order, that's okay, I can do the first order, but I need to generate epsilon in front of everything. This is the point. If you don't have epsilon, how to do it? Well, I can change the time scale, which is indeed the case. So I can define